All right, so I just wanted to kind of outline what we've done for this whole week, and starting with the energies that we've covered so far. So last week, we talked about kinetic energy, we talked about gravity, gravitational energy, and what we found is that in situations where gravitational energy is not completely converted into kinetic or vice versa, we always have a little bit of energy that's stored as dissipated energy, meaning as internal energy in some object, and we can never recover that energy to do useful things for us ever again. This week, at the end of the week, we actually came up with the formula for a new form of energy that we're studying, namely elastic energy. Okay, so let's just kind of review what the letters are. Remember, M is mass, V is speed, G is gravity, H is height. That's for our first ones. And of course, in this new elastic energy, we realized X is the compression or the stretching of a spring, and K is this thing that we called a spring constant. And that tells us how stretchy a spring is given the force. So if we have a low spring constant, if it's small, a spring is easy to stretch. And if it's large, it's hard to stretch or compress. So a small spring constant is like the springs that we had in lab. A large one would be like the spring in a mattress or like in shock absorbers in a car. So here's how we got there. If you remember, we did a little lab where we had a little spring hanging, and then what we did was we actually found the force, the Fs, the force in the spring, which was equal to the weight put on the spring. And we came up with this equation by plotting force versus the stretching of the spring. And we calculated this slope, which we called K. So we came up with this formula, F equals negative Kx for the force. It's negative because the spring always resists being stretched. X is the displacement of the spring from its unstretched, and F is just the force of stretching. So we were able to take that, and we did a little bit of work, and we came up with a formula for the energy stored in the spring, where we basically said the energy, the elastic energy in the spring is given by 1/2 times the same K that we calculated times X squared. From now on, this is something that we're either going to be given or I'll explicitly have you calculate it. So you never have to worry about this lab stuff again. So I'm just going to scratch that out. We're just going to focus on this formula for the rest of our time in physics. And you know what? This formula too. Here's the kind of problem we can have you solve. A spring with spring constant 100 newtons per meter is compressed 3 centimeters. The end of the spring is 0.5 mass. Assuming the force frictionless, meaning no dissipated energy, let's get the speed of that mass once the spring is completely released. So this is the perfect kind of problem that we can do. Whoa, I don't know what that was. So there we go. So again, take a second, read the question. I'd even pause the video. And then in this question right here, we'll begin. So we have all elastic energy, and we're told the floor is frictionless, so it gets converted to all kinetic. So what we're actually able to do is we're able to take this E elastic equals E kinetic, just like we did before. So we're going to have 1/2 Kx squared equals 1/2 mv squared. Now, what I'm going to do is just plug in my numbers. 1/2 times 100 times 0.03 squared equals 1/2 times 0.5 times v squared. So it's actually up to us to calculate what that's going to be. So when we go ahead and do that, that'll actually be the thing that you're going to submit on your Google Docs for homework today. So this is just a little brief introduction to what we're doing with springs. We're going to take this discussion up after we get back from spring break because we got some fun stuff planned for next week.